Lesson of 105. Oh, this will be a good one. Take out a blank piece of paper and write the word symmetry on top of it. Symmetry. And when we talk about symmetry, we talk a little bit about mirrored images, or what we call lines of symmetry. And by that, for example, we mean something like this. If, let's say you have an isosceles triangle, and I asked you to draw me all the lines of symmetry. What a line of symmetry does is it divides a shape in half so that when you fold those two shapes, fold it along that line, you'll get something that matches up exactly. So if you're talking about this one, okay, I should probably draw it. Let me draw it a little. Let me draw it a little bit more obnoxious so that it doesn't confuse you too much. Let's say I have this and this. And this is my isosceles triangle. A line of symmetry, this one has only one line of symmetry, and that is right down the middle. Okay, because that would cut it into two equal pieces. If I folded it on that line, they would match up. Now you might say, well, what about the other places here? Well, this does kind of go down the middle, but I can guarantee you that if you folded this along that line, this corner is going to end up over here as opposed to lining up with that. So it is not a line of symmetry. This one has only one line of symmetry. One line of symmetry. Now, there are some triangles that would have three, and that would be a triangle that looks like this. If you had an equilateral triangle where all three sides were equal, how many lines of symmetry do you suppose that's going to be? Well, you would still have the one that goes right down the middle. You'd have the one that goes down the middle splitting it this way, and you'd have the line of symmetry that goes down the middle splitting it that way. This one has three lines of symmetry. Because you could fold it along any of those and it'll match up. So let's take a gander. Let me find something here. Here's our example demonstration. Let's say we're talking about a rectangle. Where would you suppose a line of symmetry would be? Okay. Horizontally or vertically? Horizontally. And that would be, I suppose, true because if I do this, if I fold this along this line here, those two sides do match up, corner for corner. Another line of symmetry, Maggie? Yeah. A line of symmetry vertically like this. Fold it here. I will get it there, vertically there. And yes, it does match up nicely there. Correct? Diagonally. Now, before you jot that down on your paper, let me show you what happens diagonally, because diagonally actually is not a line of symmetry. Take a look. I'll show you what happens. If I go on the diagonals of a rectangle, mind you, this is not a square. If I go along the diagonals of a rectangle, best I can. I missed by a little bit, but this is what happens. They don't match up. They go kind of down the middle, but the corners don't match up. Okay? So this, a rectangle only has those two lines of symmetry. Look. And, or if you did something like that.
Hey, that's what I said.
Now a square, if you have a square, that one will, if I rip this piece of paper into a square, 8.5 by 11, how much bigger is that wider than it is? 8.5, 2 and 3/4 I have to rip off. If you do have a square, which this is not anymore, just by a little bit here. Still not a square. If you do have a square, you can do the diagonals actually. As a matter of fact, that's how they figure out if something actually is square, is if their diagonals are equal. I think I'm gonna miss it again. Okay, if you do a square, if it is in fact a square, that would be, you would have another 2 lines of symmetry. So how many lines of symmetry does a square have? A square, you'd have 1, you'd have 2, you'd have 3, and you would have those 4. And then one last one, what about a circle? Lines of symmetry of a circle. Isabel?
Down the middle.
Down the middle vertically. Joe?
Side or horizontal.
Horizontally. Kate?
Diagonally.
Diagonally. Both ways diagonally. So that means a circle has how many lines of symmetry? Well, tell you what, wouldn't this be a line of symmetry? 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 Wouldn't that be a line of symmetry? A circle has an infinite, never-ending lines of symmetry. You could never stop drawing lines of symmetry because anything that goes through the middle and is a line would be a line of symmetry. Okay, I think that's, let me see if they go into anything else here. All right, good. Now, along those same lines, okay, there is something that's called rotational symmetry. Now, I'll put it under symmetry. And rotational symmetry is a little bit different, but you can probably figure it out based on the word that it says there. A figure has rotational symmetry if it regains its original orientation more than once during a full turn, which means this. If, when you spin it, you get the exact same shape, and here's the key, before, just underline, before making a full turn. Okay, and I'm going to go to my shapes and I'm going to do this here. I do a triangle. Well, let's do this one. Let's make it a red. Okay, so that means this. Let's say I'm starting with this triangle here. Calling that thing. Let's stop closing. If I'm clone here, hold on a second. Turn off the clone here. Okay, so here is, there is my triangle there. Something has rotational symmetry if it ends up looking exactly like this, pointing up, same direction, same everything, before you spin it all the way around. So I take this and I spin it like this. You know, it doesn't look, it doesn't halfway here, still doesn't match up, still doesn't match up, still doesn't match up. This isosceles triangle does not have any rotational symmetry because it did not look exactly like it did until I made one whole turn. Any shape after you make a whole turn is going to look just like it did when you started, okay? So let me give you another one. Let's say Well, let's do an isosceles, or an equilateral one. Tell me when you think that looks equilateral-ish. That's pretty close. Clone. Clone. Where's my clone? Clone. Okay, so let's say I've got this, okay, and I spin it. And, uh-oh, what happened to my clone? Let's just copy and paste. Copy, paste. Okay, so let's say I've got this one right here, and I spin it. Alright, still doesn't look like it, still doesn't look like it, still doesn't look like it, but when I get it to here, sorry, it should. I don't know why it doesn't. Oh, it's because it wasn't exactly as nice as maybe. Let's see if I can get it to look like that. If it was actually an isosceles triangle, it would have some exact spaces of rotational symmetry here. This one's supposed to have a couple, but something went haywire with my thing. Maybe I'll try a square. Try a square. Let's try a square. Do we get a square? There's a rectangle. Let's try a rectangle for a square. I also think it's because my board isn't, you know, you guys don't care. A square, children, should have rotational symmetry. It should have rotational symmetry when it gets here. Well, the problem is more so with my board, because it's not my board and my computer screen kind of wipe out. Let me see what happens. Let me try this. Let me try this. We might get to rotational symmetry yet. See how that circle looks like circles? I think this will be better. It's the technological issues we have with it. Okay, starting new board and a square. Let's try a square again. Tell me, what do you think that looks like a square? Let's say that looks kind of like a square. I'm going to copy it, paste it. Hopefully this is better. Okay. A square has rotational symmetry because when you get a quarter of a turn like this, it's closer, not quite there, it would be the same. Another one would be the same here. Well, this one already did when I got to there. And this one should be when I get to there, and obviously when I get to there. So a square has rotational symmetry. I don't believe they'll ask you how many rotational symmetries. They'll ask you if it is rotational or if it isn't rotational. They also give you something like this. The letter M. Wait, sorry. I have to do it like this. The letter M. Does the letter M have rotational symmetry? In other words, when you spin it, will you get the letter M before you spin it a whole way once?
No.
Let's look at, this should be easy to see because I just put my little, and I spin it. See the letter M yet? No, looks like the sigma. Now it becomes a W, then it becomes E. Yeah, no rotational symmetry. How about the letter A? I'm going to do this. Rotational symmetry? Does it look like an A? No, A, no, A, no, A, no. It's kind of slow. No rotational symmetry. But what if I asked you if it had reflective symmetry, which is what we talked about before?
Yeah.
I think it's stuck. Uh-oh. We may have pushed the board to its limits. No.
What happened? Notebook has stopped working. Because it doesn't like us.
It's coming. Give me a second. Let's try that again. Let's try that again. So, like I said, the letter A did not have rotational symmetry, but does it have reflective symmetry? Could you draw a line that would split it in half so that when you folded it over on its side, it would be?
Yes.
Maggie Stewart, it would be where? Yep, a vertical line right down the middle would split it. Okay. Back to the letter, how about the letter T? Oh, actually, I have to do it in one fell swoop here. Hold on. The letter T. Rotational symmetry?
No.
Does it have reflective symmetry?
Yes.
Yes. Wait, on the last one here. What about the letter H?
Yes.
Rotational symmetry?
Yes.
Yes, because when you get it to here, it is the same letter H as it was before. Does it? How many lines of reflective symmetry does it have? You could split it like this. You could split it like this. Can I split it like this? No. Look at page 690. I'm sorry, 690. Just so you can see it, so I don't have to necessarily draw it. The book gives you an example problem that looks like this and says, is there a line of symmetry between those two? In other words, if you fold it somewhere, will they fold up on each other? Yes. And that line would be where? Where would the line of symmetry be so that when you fold, Elijah? Right in between them here. But they want you to realize that, yes, this has a line of symmetry, but if the shapes look like this, if you look on the next page there, if they were both identical like that, does that have a line of symmetry? No, because if you did fold them along that same place here, this little jutting out piece would actually end up sticking out over here when you fold it over. Yeah, so you got to kind of look at it kind of closely when you do it there. Yeah, that's fine. Oh no, do look at page 692. Look at letter G. Are you looking at letter G?
Yes.
If you saw this problem on your homework, notice what it says. Copy this grid and figure on your paper. And since you have homework paper that has grids and we've signed our little contract that says we will do this, you would get this little shape that looks like this. Wait, it went up to, how wide is it here? 1. It looks like this. And this is all shaded in, right?
Blue.
Blue. And the book said, draw the image of your figure reflected across the horizontal line Y3. So here's Y1, here's Y2, here is Y3. And what they're telling you is this. Notice how we talked about folding and flipping and matching up here. They want you to draw this little U shape so that it's a reflection right here where Y is 3. And the question I have for you is how or where, how would that look if you did that? If you took this piece of paper and folded it and flipped it up, where does this shape end up here? Because that's where it would end up. Elijah, what would you say?
It would be round and line.
Well, here's the deal. If this is a piece of paper and I fold it right here and I flip it up, see this space from here to here? There's also gonna be that same space right from there to there, because it's gotta be match up. So, because this has to have that same space there. Same thing here, this space, that gap of 1 here, has to be that gap of 1 there. So this bottom line here would actually match up right here on something, correct? And then what's gonna happen from here up here, how high is that gonna be? It's gonna be this same distance here, 1, 2 high. This, it's kinda like the opposite, this goes down 2 right there, so this is gonna go up 2 right there. What's the rest of it gonna look like? Isabel? Over 1?
Yeah, over,
Up?
no, over one and then down.
And then down 1, over 1, up 1, down 1. So this shape is a reflection. Sometimes reflections are a little tougher to tell there, but that's perfect.